We're covering section 6.3 today. We start out with the last example from 6.2 we didn't cover last time. Okay, so we'll go through this and then we'll get started with 6.3. So in this example, in the figure, D, E, and F are midpoints of triangle ABC. We have to prove that ABC is similar to EFD. Alright, so how we can do this is we can say that since D and E are midpoints, so that DB is going to equal 1/2 of AB, and BE is equal to 1/2 of BC, right? Yes. Okay, so I'll give you a second to get that written down. Okay, so angle B is congruent to angle B. So then, since we've got the 1/2 and 1/2 ratio on the sides and the angle B, the included angle, is congruent, we can say that triangle BDE is similar to triangle BAC by side angle side. Thus, we have DE is equal to 1/2 of AC. And then we're going to do the same thing on the other smaller triangles, and we would show from that, like above, there we go. We've got DF equal to 1/2 BC, and EF equal to 1/2 AB. So then that makes, in that middle triangle EFD, all those sides are 1/2 the lengths of the sides of the larger triangle. They all have the same proportional, so we can say, therefore, triangle ABC is similar to triangle EFD by side, side, side similarity. Any questions? All right. Now we'll go on to the other notes. Okay, it says, do not let what you cannot do interfere with what you can. That's John Wooden, famous basketball coach of UCLA from Martinsville, Indiana. 6.3, applications of similarity. Objectives, use mean proportional to find lengths of sides of triangles. Use the side splitting theorem to find lengths and sides of triangle and then define mid-segment. Okay, so with this mean proportional right triangle, okay, it's asking us to name 3 pairs of similar triangles in the figure. We're going to actually draw the 3 triangles separately. So what I have here is, okay, this triangle, this is 30, this is 90, so we know that this angle has to be what? 60. Same thing in this other triangle, right? This is 60, this is 90, so this has to be what? 30. Right. So essentially I've got 3 30, 60, 90 triangles. So by angle, we know these triangles are similar. But it gets confusing with matching up the similar sides unless you draw them separately. So if you need to, they ask you to name the similar triangles, you can draw them separately. I'll draw these separately. So we'll take the initial overall big triangle, right? It's PQR, and then we take the medium-sized triangle, and in the medium-sized triangle I've kind of got to turn it around. Okay, so the right angle is right here in the medium triangle, so that would be S. The short side is SQ. Here's the short side in the drawing I'm making, so we would call this Q, and then the remaining side is R. And then in the smallest triangle, we'll turn it the same way as the others. Okay, so the 90 again in the smallest triangle is at S. The shortest side, what's this point here going to be? Right here, what's that point down in the bottom left going to be? Yeah, it's P. The short side of the smaller triangle, that'd be P. And then the other one, the remaining side would be, point would be Q. Okay? Now when you name them, it's very easy. Everything matches up, right? So I can say, for example, angle, triangle PQR is similar to triangle PSQ. I compared the big one to the small one. They're similar. We can say triangle PQR is similar to the medium-sized triangle. And so I started at P and went clockwise. We start at Q on the medium size, and it would be QSR. And then we've got PSQ, the small one. It's going to be similar to the medium-sized triangle, QSR. Right? Questions on matching up these similar triangles when we have one triangle drawn like that? Everybody has it? Okay. So, Theorem 6.9, in a right triangle, the altitude of the hypotenuse is the mean proportional between the two segments formed in the altitude by the altitude of the hypotenuse. This is called, we'll call this the t-test, right? So it's a pattern. We've got, so we're taking the two smaller triangles. We've got AD, which is the long leg of the medium-sized triangle, so it's a long leg. The long leg is to the CD is its short leg, as the CD is the long leg of the small triangle, is to the short leg of the small triangle. So that's how I'm setting my proportion. But you don't need to really worry about that if you use this, what I call the T method, to solve. So when I have a triangle, and it involves a triangle with this altitude drawn to the hypotenuse, and it involves this middle segment here, we're going to use the T method. The T method is, when I set up my proportion, it's going to make a pattern of a T. I say AD is to CD as CD is to DB. I make that T pattern. That tells me, so I'm going to just follow the order that I do the T in. AD is to CD as CD is to DB. Right? T method. So in the right triangle, CD is the altitude to AB. Then, so that's the T method. Let's look at an example, and then we're going to introduce another method. So in the right triangle, ABCD, we've got AD is 5, AB is 8. They want us to find CD. So we're going to, if AD is 5 and AB is 8, what's DB? Yeah, it's going to be 3. And we'll call this DC, what we have to find, or CD, we'll call that X. Alright. Somebody set it up with the T method for me. What would my proportion be? Jatiz?
5 x is x to 3.
Yeah. We'd say 5 is to X, 5 over X, as X is to 3. Right? And then we'd cross multiply and solve, so X squared equals 15, so X equals radical 15, and we know X is equal to CD. So I found CD. That's a way we can do the T method. Now, we can also find, everybody have that? We can also find AC. Let's clear this up. Or I could find BD. Let's find AC. We'll call it Y. Okay? Now, this when we do this method, it's called the Nike swoosh method. Nike swoosh method. Because it's like it makes a Nike swoosh. So you're going to take your long side, your hypotenuse, right? And you're going to say, the pattern is, you say 8 is to Y, as Y is to 5. See, it kind of makes a nice swoosh. That's the Nike swoosh method. 8 is to Y as Y is to 5. Cross multiply solve, so Y squared equals 40. So Y equals 2 radical 10. which is equal to AC. Questions on the Y method, or the Naik-Swoosh method? Okay, side splitting theorem. The side splitting theorem says a line parallel to one side of a triangle forms a triangle similar to the original triangle and divides the other two sides of the triangle into proportional corresponding segments. Alright, so here we have DE is parallel to AC. So we know by angle, these top and the bottom are going to be similar. So we can say that BD is to DA. You don't have to use the whole side. You can do this part is to this part as BE is to EC. So you split up the side. That's the side splitting theorem. Looking at an example. So in the triangle, we'll label our parts. AD is 4, DB is 6, EC is 3, EB is X. Right? Somebody want to set up the proportion to solve this? Somebody besides Shatiz? Nina.
6 over 4 equals 6 s to 4 equals x s to 3.
Yeah. 6 over 4 equals x over 3. Cross multiply. 4x equals 18. X equals 18 over 4, which is 9 halves, which is equal to EB. That's what we had to find. Questions? Okay. So in the triangle, DB is 7, BE is 5, EC is 2. What's AD? Somebody set up that proportion. Okay, go ahead, Zachary. 7 is to x is 5 is to 2. Cross multiply 5x equals 14. So then x equals 14 over 5. Right? And that's equal to AD. Questions there? All right. Let's look at another example. We've got DB is 5, DE is 6, AD is 3, AC is, we'll call that Z. Somebody set that up. Okay, Shatiz?
It would be 5 as to 3 equals, let's see, Z as to 3, wait, 6.
No, you have to be careful. Somebody else, Nick?
5 is to 8 and 6 is to Z.
Right. Okay. The side splitting theorem doesn't apply here because the 6 and the Z are not part of the split side, right? It does not make sense to say 5 is to 6, the whole side of that small triangle, 5 is to the entire base, 5 is to 6, as part of the side of the big triangle is to its entire base. You see how it's not an apples to apples comparison? So if it involves an entire base like that, and it's not split by the parallel lines, you can't apply side splitting theorem. This is important because it causes a lot of people to miss points. Does everybody understand what I'm saying? Everybody see what I'm getting at? So Nick was right. We would set this up as, we would say 5 is to 6 as 8 is to z. The entire length of the side, 8 is to z, and then we cross multiply, we get 5z equals 48. So z equals 48 over 5. Any questions? Mid-segment theorem. Mid-segment theorem. The segment that joins the midpoints of two sides of a triangle. Theorem 611, mid-segment theorem. A mid-segment of a triangle is parallel to the third side and half its length. So we've got the mid-segment is parallel to the third side and half its length. So DE would be half of AC. These lines are parallel, and DE is half of AC. Everybody get the idea? All right. So we're given triangle ABC with mid-segment DE. We're going to prove DE is parallel to AC, and DE equals 1/2 of AC. So in the informal proof, we'll just do an informal proof. Let's say we've got triangle ABC, the overall big triangle ABC is similar to triangle DBE because angle B is congruent to angle B, right? Angle B is congruent to itself, and the corresponding sides that include the angle are proportional. BD is to BA, and BE is to CE as 1 is to 2, because we know those are 1/2 because of the mid-segment. All right, so that's a side-angle-side congruence, similarity. Then by corresponding parts, angle BAC is going to be congruent to angle BDE, because we know in similar triangles the angles are all the corresponding angles are the same, and so then after we say, so we've got these two angles congruent. So then by corresponding angles, DE is parallel to AC. Right? And then also, to finish it up, make sure everybody's gotten this written down. I'll wait a second while you're writing. Anybody still writing? Raise your hand. Okay. Then we can say also DE over AC is equal to 1 over 2. So DE is equal to 1/2 AC. Just like, and that's the other thing we had to prove. So since the other sides had a 1-to-2 ratio, we know the third sides will have a 1-to-2 ratio. Questions there? Okay. Mid-quad theorem says, and if we have a quadrilateral A, B, C, D, E, F, and G are midpoints, as shown, then E, F, G, H is a parallelogram. All right, so it's saying if you connect the midpoints of the sides of a quadrilateral, they will form a parallelogram. That's the mid-quad theorem. Questions there?
Will any quadrilateral apply?
Any quadrilateral? Yep. All right. So that's it on the notes.